Hello and welcome back everybody to the Towards Data Science podcast. Today we are talking to Daniel Filan, who is an AI alignment researcher at Berkeley and the host of AXERP, an AI alignment podcast that you should definitely check out right after this episode. We're going to talk about Dan's research, but also his motivation for getting into AI safety, his involvement in effective altruism, and why that's led him to, among other things, place bets on the outcomes of presidential elections. So Daniel's research is actually really fascinating. It involves studying the structures that neural networks form internally as they learn to try to understand neural nets better and also, hopefully, to make their behavior safer and more predictable. So we'll explore the importance of interpretability for safety and what may be the deep connection between safety research and capabilities research as well. But I think that's enough of a preamble for this one, so without further ado, let me step out of the way and let the episode begin. All right. Well, Dan, thanks so much for joining me for the podcast.
Thanks for having me on.
I'm really excited to have you here. There's so many interesting topics that we could discuss. Obviously, you're doing some really interesting research under Stuart Russell's supervision at Berkeley, and I think we'll dive into that. But I think what's really cool about you and a lot of the people in the space generally is that you tend to fall into this bucket of concern, thought, and philosophy that is called effective altruism. And I wanted to start there, just to talk about the way you see the world, the way you decide what to work on, that sort of thing. Maybe we can start with just like your thoughts on how would you define effective altruism, and how does it affect the way you think about how you spend your time and on what?
Yeah, so I guess effective altruism is this, philosophy in the kind of colloquial sense of like trying to think carefully about how to do the most good with like the limited resources you have available to you. So I guess implicit in that is a couple of ideas, like the think carefully sort of implies that the answer might not be obvious.
Right.
Or like, well, because there's definitely some world, like you could imagine a world in which like the important thing is to just like try and do something good. And like most things you could do that you would think of as trying to do good are like approximately as good, or like as good to, maybe some are better than others, but like you're way better at some than others. So like, you should focus on those. So I guess one premise of the effective altruism idea is just that like, there's some opportunities to do good that are like way, way better than other opportunities. The second premise is it's not obvious which ones those are. So I guess, and the third idea is one of efficiency, right? The natural way to think about philanthropy or doing good is like, oh, let's like think of a problem and like maybe you check like, okay, is this like a really important problem? And then you kind of stop there. Like you find an important problem, work on it. Whereas the effective altruism approach, the effective part is very interested in this idea of like, okay, but like, how much change can you make,
Right.
Because you only have so many dollars in your bank account. You only have so many hours in your career, if like that's what you want to use your career for. So like you sort of want to be in some kind of maximizing mindset with respect to that. So that's basically, I guess, the intention of effective altruism. The extension is there are people working on a bunch of different things. So a lot of people who are interested in global poverty reduction or like trying to improve health outcomes in developing countries. There are a lot of people who are interested in reducing the number of animals who live on factory farms. There are a bunch of people who I would count myself among more who are really interested in reducing the possibility that humanity might go extinct or otherwise like kind of be locked into a pretty bad future, like much worse than we could have. And then there are also a bunch of people who are like, we should think more. Maybe we haven't come up with the best idea yet, so let's just analyze some stuff.
Yeah, sort of a whole portfolio approach to this kind of altruism stuff, right? And I mean, with that, when you hint at the fact that these problems, the problems that are worth working on, are non-obvious, I think one of the things that comes with that is a certain level of intellectual rigor, and in particular, a focus on probabilities and analysis. Bayesian probability theory, applied Bayesian probability theory, really.
People try to do that.
Right, yeah. So that's kind of where I wanted to go with this. What do you see as the ways in which effective altruism requires that you pull in this sort of statistical lens? And what are some of the ways you apply that lens in deciding how to spend your time?
Oh, that's interesting. I guess I think maybe one view I have that is perhaps uncommon in the machine learning community. I don't know how uncommon it is, but I basically think that like machine learning, like figuring out what good ways are for AI systems to reason. I think if that doesn't change how you think you should live your life or something, then either you're wrong or the theory isn't good enough.
Mm.
So in terms of like how I think about the importance of using Bayesian probability for effective altruism, like kind of think of it as important for just like having good beliefs in general. But I guess the specific case, yeah, so specific to effective altruism, right? There are a bunch of things where like you don't like suppose you want to know, suppose you're interested in this problem of like, okay, it turns out that a bunch of people in the developed world have worms, worm infections. That's a thing that can happen, unfortunately. And like, it kind of sucks. You know, it means that you can't go to school as much, is my understanding. It's definitely unpleasant. And so the question is like, okay, one thing you could potentially do is you could give people deworming pills, and like, you know, I believe the way you do this is like, you go to a school, you give the school a bunch of deworming pills, you like tell them to hand them all out on a certain day, like maybe you help with the infrastructure of that, and then you know a bunch of people get dewormed, and the question is, okay, what happens next, right?
Mm.
Like how, firstly, like does that make people less, you know, are they less infected with worms? And you know, are there any like weird side effects or something? Um, secondly, secondly, getting to the Bayesian point, you don't just want to like reject the null hypothesis or not, right? You care about the magnitude, because if it costs like $10 to buy a pill, and the pill makes, and you know, every $10 you spend, like there's a 1% chance of one person feeling like 1% better, that might not be worth it.
Yeah.
But you know, if the pills are really cheap and the effect size is bigger, then like that's a bigger deal. So you want to care about like, okay, what is the actual effect size? You want to care about, okay, what is the like, you don't just care about people not having worms, right? Like the reason you care about them not having worms is like maybe that'll help their education, or maybe that'll help them live longer. So you want to check, okay, like are people going to school more? Is that like helping their lives? Are
Is it
they
having the
living
intended
longer?
effect?
Yeah. Is it having the intended effects? You know, to what degree? And then you've got to say, okay, we ran this one study in one state of India. Can we now do this in some other place? Will that have the same effects? And the answer is like, well, you've just got to like think about, like the answer is not going to be definitely yes or definitely no. It's inherently kind of a probabilistic question.
Yeah.
So yeah, I would say I think it especially is true for things more like the global poverty side, where like you really can, like some people do run RCTs. Um,
Sorry,
I'm very
RCTs?
interested. Randomized controlled trials.
Oh, yep.
So like, yeah, some trial where you give some people a deworming pill and you give some people a sugar pill, and you see like, okay, you know, is there a difference in what happens? And you randomly pick which people you give which pill. So I'm really interested in reducing the chance that humanity goes extinct or is like locked into a really terrible future. For that one, it's a little bit less statistical because we don't have many experiments of that one.
Right.
There's some like conceptual Bayesian thinking, I guess, where you have this idea of like, oh no, I've got like, you should kind of think in probabilities, and you like should try to like increase your credence in theories that like predicted with a high probability what you actually see. But you know,
It's hard to make those predictions in the kind of landscape and with the limited information we have right now for that sort of thing, right? I mean, this is, I guess, as you say, this is like one of those big differences between the existential forward-looking risk that we face and the current deworming poverty reduction stuff where we actually have data. I'm curious about like that aspect. There are a lot of arguments that, make the claim that either we aren't going to reach the levels of technological capabilities that would be dangerous. I'm talking here about AI specifically, because I think that's the context that we're both thinking of it from. But there are a lot of claims that either, we won't reach that level, or if we do, somehow safety is going to automatically come with capabilities. So you just won't be able to build a super powerful AI system that isn't already equipped with like what some people call common sense, or some notion of ethics, morality, that wouldn't be super moral in addition to being super intelligent. And in particular, I think that was the argument that Melanie Mitchell made on the podcast a couple of episodes ago. She, of course, debated Stuart Russell, who's your supervisor. So I'm sure you don't have like a telepathic link to Stuart, but to the extent that you're able to, I guess, summon your mental model of him and maybe parts of your own as well as you think these things through, I'm curious, like, how would you interact with those arguments that say either, we're not going to reach that level, or if we do, it's going to be done in a safe way, almost intrinsically?
Yeah. So, I mean, in terms of we're not going to reach that level, we sort of know that there is one physical system that can achieve human levels of intelligence, at least as long where you define intelligence as the thing that like makes changes to the world. That's humans, right? Like, I guess I don't see why, like the impossibility claim, it's difficult for me to see how that could really hold up. A different claim you could make is like, okay, well, maybe it's possible, but like it might just be like 1,000 years from now.
Right.
It might just be incredibly, incredibly difficult. And basically, my answer is like, well, I think if you think about, okay, what can machine learning do now? And like, how much would we have to train? Like, how big would things have to be? And how much would we have to train them in order to get to the human level? Even if you have like pretty pessimistic bounds on that, like if you think like, oh, we have to like redo all of the like neuronal computation that evolution did for like since, I don't know, the jellyfish first existed or something, like more computation is becoming cheaper and cheaper year by year. Like it really seems like as far as I can tell, when people like try carefully to forecast this, it's probably going to happen in the next 2 centuries. Like I find it difficult. I don't know, maybe it's possible that I'm missing some like really clever argument against, but like, yeah, as far as I can tell, I think we have pretty good reason to believe that like sometime that there's like, well, a decent probability, to call back to the previous point, that at some point within the next 100 years, I think we could probably do it. In terms of whether like a really smart thing would be super moral, yeah, I guess I kind of buy the like it goes by 2 names. One is the Humean theory of motivation, and one is the orthogonality thesis. So basically, what they say is like the things that I might be butchering the Humean theory, but I might be getting it approximately right. What they say is that like, look, you can like be smart and have like a wide range of goals that you want to pursue. So like I think one reason you might think that really smart things would be super moral is that they would like figure out like the moral facts, right? Like they'd be able to like reason about what humans want and like what humans ought to want and stuff, and they'd be able to like come to true conclusions about these. But it's not obvious that like those true conclusions would be motivating, right? Like
Motivating in what sense?
Like suppose well, some people doubt this, but like let's suppose that there is just a matter of fact about what's right and what's wrong. And let's suppose further that I think about it a lot, and I come to the conclusion that like actually eating ice pops, like these icy snacks, they're like sugar water in tubes that you freeze, that eating these is just like inherently morally wrong, right? Well, then it's not obvious that would make me not want to eat them, because the reason that I want to eat them is that it's hot and they would cool me down, and I have all these reasons for wanting to eat them. And like the fact that it's morally wrong, like this, like it seems like I could just not particularly want to do things that are morally right, or at least not want to do it enough to, give up this chance to get this delicious icy pop. Now one I think one way that could be false, and one way that it is false for humans, is that what's morally right is like really closely linked to like kind of achieving a wide range of goals. So like I think like, for instance, why should people be honest to each other? I think that just basically makes society work better. I think like, you know, mostly your life is just going to be better if you're honest to people, right?
So,
But like if you're much more powerful than all humans, like maybe you don't have to play by their rules. So that's
yeah.
basically my response to those two ideas.
I definitely agree with that frame. I think the tough thing is I have the same biases as you, so I do want to remind the audience, if you want to see that other side of this argument, definitely check out that Melanie Mitchell podcast or the one with Oren Etzioni that we just put out. So I am going to agree with Dan here, and you're going to get a little bit of propaganda, but that's okay. I definitely align with where you're coming from here. Also at the level like human beings, we look at some of the most disastrous regimes in human history, and they were run by objectively very intelligent people. Hitler was brilliant. Stalin was brilliant. Pol Pot was brilliant. These are charismatic, intelligent people. On any IQ scale, by any measure, I'm sure they're going to be in the top, 20th percentile, maybe even 10th or more. And yet you have these wildly divergent moral outlooks. You can debate whether they were sincere about particular kind of moral framings, but certainly some of them were. There have been highly intelligent, sincere people who've disagreed profoundly about what's morally right. So, like, I guess that's the sort of orthogonality in the orthogonality thesis, right? You can decouple intelligence or capabilities, like from
Yeah.
moral.
Yeah. I guess you might think that, like, look, Stalin was really bad, but like maybe he wasn't smart enough to really understand the true morality. So I don't think that
Right.
like that's a totally knockdown argument, but perhaps it's illustrative.
Yeah, well, I guess, yeah. My intuition here is something like, even if, so there may be a lot of optimal points for society, local optima, that are approximately as good, and it's really hard to tease apart from the outside, like which one is better. And they might all have really, really different moral norms. Like in some cultures, arranged marriage might be, the default norm, and that it might be possible for those cultures to attain an average level of happiness or a median level of happiness that's just as high as any other, and yet they look completely different, sort of from the inside view. So it's I guess this is where my intuition kicks in, at least on the human level, and obviously these things have limited domains of applicability when we're talking about superintelligence, but I don't know. That's kind of where my mind goes. Do you think these human analogies are dangerous though? Like, is there a risk when we start thinking in these terms, like I just did, that we start to overgeneralize based on human failings or human thinking?
Yeah, I mean, I guess you just have to take humans as the evidence that they are, which is an existence example, and like, people have about this range of capabilities, and they can do that. They have, this thing happened with humans, and it's really true that that thing happened with humans. And if we expect AI to be like really similar to humans in the relevant sense, then that's strong evidence. If we don't, then it's weaker evidence, unless we derive a like really powerful theory from humans that we are like pretty confident that that theory holds in general. Yeah, I don't know. I think like you can. I think some people like. I think it's easy both to draw too much on the lesson of humans and to like not draw enough on the lesson from humans. Yeah, I don't have a super strong opinion about like which way people are more.
Yeah, it's frustrating when the right mature answer is moderate, and that happens so often. I want an extreme, yeah. Well, but okay, before we get into the details of your research and some of your work in AI safety, I do want to ask one more question about this broader kind of EA space and some of the ways of thinking in effective altruism. And this has to do with betting. So every effective altruist I talk to loves to talk in terms of probabilities, and I love that. I think it's super constructive. But there's a specific kind of approach to leveraging probability theory that is this kind of skin in the game betting approach that I know you've kind of gotten involved in. So where does betting fall into effective altruism? How has it helped you think more clearly about the world?
Yeah, I think of betting as a habit of mind that's like generally useful when you're not just for effective altruism, but when you want to have true beliefs, and in particular, if you want to have like a community of people who have true beliefs. So basically, when I say betting, I don't mean like betting on horses necessarily or sports.
Yeah.
I mean like suppose somebody says something like, "Oh, I think like I kind of don't want to use a political example, but mostly people like say very overconfident things about politics. So let's say, oh yeah, the Democrats are sure to win in the midterms. I'm like, you know, they've got this. Like I think people can often be very overconfident about that, and I think when you ask somebody, okay, do you want to take a bet at like 3-1 odds, where you pay me $30 if the Democrats don't win, and I pay you $10 if the Democrats do win? I think there are two effects of that. Firstly, if I just said the Democrats will definitely win, I might not have been thinking very carefully. But when a bit of money is on the line, I'm like, oh, is it like 3-1? Well, maybe it is. Maybe it's not, right? So firstly, like, it just causes you to think a little bit more. And the flip side of that is it's sort of a tax on like bullshit, basically.
Yeah.
Like I think one problem with the world is like, I don't know, a lot of people say a bunch of stuff and it's not obvious like when they're like, you know, when they're just bloviating, or when they're just like saying what's popular, or like versus when they're like really trying to get at the truth. And like, you know, the more people bet against bloviated claims that like have nothing to do with reality, I don't know, the poorer those people get, and like maybe the less bloviation we have. I think another advantage of it is like when you have like especially when you have a liquid betting market, when like you know, it's not just like that one guy you bet against about the midterms, but when a ton of people bet against each other about the midterms, then like you start getting a sense of like, okay, what's like the sort of market probability of this thing? And there's reason to think that like if a bunch of people are betting, like that probability is going to bring out like a bunch of information that's available to bear on that probability, because like the individual traders will like, you know, trade based on what they know, and that should come to some equilibrium. So it can be informative in that way, which I think is good. Oh, the other benefit of, and similar to that, I think betting has this opportunity to like give you a sense that you might be wrong about something. So there's one person in the EA space who was pretty, there was recently a story about like there potentially being life on Mars. And there was one person kind of in the EA space who was like, oh yeah, I think there is. I'm willing to bet.
By any chance?
This is, yeah, I wasn't sure that I wanted to name or shame him. But it is Robin Hanson. And yeah, somebody was like, I'll take you up. And then Robin said, yep, sure. And then like a bunch of more people were like, oh yeah, I'm willing to bet at like big amounts of money. And then he was like, this is one of the signs that you're wrong. So the kind of market forecast can be useful not only for a disinterested observer, but if everyone's willing to bet against you, then maybe that gives you a sense that like you might be the one who's wrong.
Well, to Robin's credit, and I think to the credit of anybody who engages in this kind of activity, it really is like, I mean, it's the only way to make contact with the unforgiving. You get that jolt of, you know, when you're signing the metaphorical check and actually saying like, you know, you're almost developing that muscle memory of writing "I was wrong" and then handing it over to somebody else as penance. And I imagine that, do you find that serves like a useful role in actually causing you to follow through and update your mental model of something, rather than just going like, well, you know what, I was wrong, and it's, you know, it's an odds game, maybe I was wrong by chance, which you could have been. But like, there's something about that activity of kind of conceding in, not in writing, but in dollar form that makes it a little bit more poignant.
I think sometimes it does and sometimes it doesn't. So I've definitely made bets that I've lost where I thought like, well, it was still the right bet to take.
Yeah.
So for instance, I think it's a matter of public record that I bet against this guy, Brian Kaplan, about what vote percentage the Libertarian candidate would get in 2016. And the thing about betting against Brian Kaplan is that he's a guy who has made tons of public bets, and he's won, I think, literally all of them, or all of them that have resolved. There's one about climate change coming up that I'm pretty sure he's going to lose. But so I did the foolish thing, betting against Brian Kaplan, and I lost. But apparently I didn't learn my lesson, because I'm still like, you know, I think I was betting based on a pretty good forecast. And Yeah, but there are some bets where I'm like, oh, okay, that source of information wasn't as good as I thought.
Well, do you find it motivates you to go to the other person and say, okay, what was the mental model that you were using? And can I learn something from that? One, now that we have the evidence that it seems probabilistically to have been more right than wrong?
hmm, I think people love talking about their mental models, or at least people I know. So normally, like, I'll have heard it beforehand, and like
Mm,
the update will be like, oh, I guess that was actually reliable, and whatever reasons I had for thinking that it wasn't weren't didn't hold up. Also, I should say, like, a lot of the bets I make, like the majority of money that I bet, has been on Predicted. So that's this US platform for it's mostly about predicting US politics. Um, and it's nice in that like you can bet more on Predicted than you can with your friends. But unfortunately, like you can't like find the people who bet against you and like ask them what they were thinking. You can go to
right.
the comments section, but like that is extremely low quality on that website.
It's all ultimately, I guess, about, or at least in part, about skin in the game. That seems to be a big part of this. And maybe that's a good segue into something we all have skin in the game for, which is this question of AI safety, or at least in principle, depending on how this bet comes out, we're all going to be in the same boat. We're all going to have some stake in it. So you're working at Stuart Russell's lab. You did, I think, an undergrad studying RL and deep learning before. Did I get that right?
No, I did my undergrad. So actually, during my undergrad, I mostly studied math and physics.
Oh,
I
okay.
didn't. Yeah, I did an honors year that was studying like this, like very, I don't know, this kind of abstruse theoretical aspect of you know, supervised and reinforcement learning. But it is not meaningfully. Yeah, I did not really meaningfully study deep learning or very much practical RL in my undergrad at all.
So it was a real pivot then once you got to Stuart's lab and you're like, all right, let's do this safety thing. That was a big change.
Yeah, well, it was a big change in what I was doing. Sort of starting in the middle of undergrad, I kind of knew that I wanted to make that change.
Hmm.
And sort of it like took me a while to work up to it, you know?
Was that because you like I guess you read the super intelligence or some Eliezer Yudkowsky stuff that got you thinking about AI risk or
Yeah, superintelligence had not been published at that point.
oh
So
okay.
it was yeah, some Eliezer Yudkowsky stuff. So he's um I want to say blogger, but also AI researcher, who wrote this thing called the sequences, which I highly recommend to people, by the way. They're mostly not about AI alignment. If you find people who talk about AI alignment really annoying, you might also find the sequences really annoying for not because they're about AI alignment, but because there are certain habits of speech that some people find annoying. But anyway, yeah, it was based on like reading some of that stuff on this website called Less Wrong. Also like talking to a friend about it. Yeah, and so yeah, I got this idea that like yeah, maybe this was like a real big technical problem, but also one that like you could you could make some headway on solving. And I was like, huh. When I started my undergrad, I kind of wanted to be a theoretical physicist. Um, and I was like, well, both of these paths are kind of mathy, and one might save the world, and one is really, really unlikely to.
Tough choice.
Which by the way was not the whole like if I think about it from an effective altruist standpoint, I'm like maybe I should have thought more about it, but I don't know. Ultimately, I think it was the right call.
Yeah, I mean it's I often think of and I think there's a reason that physicists and computer scientists slash machine learning people tend to have similar lenses on the world. And it's not just the math. I think there's something roughly equally fundamental about both disciplines. Like physics to me has always been a kind of an outside in pursuit of truth where you look at the world around you and you kind of go, okay, let's try to explain how this is related to that and how that's related to that. And then you kind of manually construct this giant ontology, this set of linked concepts that explains hopefully as much as you can. And then the machine learning side seems almost like inside out, where what you're doing is saying, okay, how does cognition work? How does intelligence work? And then how can we leverage that to do everything else for us? So it's sort of like similar, but I guess complementary approaches.
Yeah, definitely both of them. They're both kind of hubristic, right?
Right.
They both
Yes.
have this conceit that like oh we can like come up with like these models that like really explain reality. And I think in both cases, or like maybe they're an like in the computer science case, does it explain reality? Like not quite, but it like
Hmm.
makes good types of reality. But you can come up with these like useful models that you can really rely on,
Yeah.
as opposed to like, oh, maybe if you I'm just speculating here, but maybe if you study history, you get this idea of like, there are a bunch of people who thought they understood what was going on and they didn't. And like, really, you should just like kind of see what used to happen. And that's probably going to happen again. Yeah, I think this is related to, I think this is probably responsible for some of the great things about those fields. And also, you know how there's this stereotype that like when physicists get old, they start like saying ridiculous stuff about fields that they aren't in. Like I remember seeing this paper about using the Ising model to predict COVID, which physicists will know that this is kind of silly, but maybe some of them will be really tempted. But yeah, I think it's a strength and a weakness.
I think this is a really good point. So just like internally at the company that I work at, so we're all a bunch of physicists. And very early, it became obvious that we looked at the world through this lens. A lens that, by the way, I mean, you said hubris, absolutely. We actually refer to this internally as cocky physicist syndrome. Like, you'll have a tendency to look at an entire field and like reduce it to a single differential equation. And you'll be like, why does this field need to exist? It's just a second order differential equation in this. And anyway, that temptation is really like, I think something that over time, hopefully you learn to walk back, especially actually when it comes to things like safety, AI safety. I find that to be one of those areas where caution and just like care and sincerity as well of curiosity just are at an absolute premium. And you tend to see that with safety researchers, like the hedging and the authentic hedging in many cases against risk. Is that something that you've seen as well? And like, how do you see that translated in like let's say the research techniques that you've explored and the ones that you think are most interesting?
Yeah, I think they're definitely more hedgy, partially just because it's not like some fields have a formalism that they can run with or have a paradigm that they can run with. And like, I guess some people think this is true of like AI alignment, but I don't, and I don't think most people do.
Can you explain what you mean by paradigm, by the way? Just I'm thinking for like non-physicists or people who aren't used to working in a field with a paradigm, because I think this is a really cool point.
Yeah, so I don't know. A paradigm might be like your job is to build a house, and like you've got to figure it out. If I were in that situation, I would not really know what to do. I'd be like, what is a house? I guess it should provide shelter for me, and it should stand up. But like you're kind of confused about the problem. Whereas there's one situation where you can be in where you're like, I know, neoclassical architecture or something. I guess you don't want that to be your house, but let's say it's neoclassical architecture. I know neoclassical architecture. I know I want columns. I know that like the job of a house is to do these 5 things. And the way you do it is you solve this problem, this problem, and this problem. And then you're done. And then you've got a house. That's kind of the idea of a paradigm. For instance, like in physics, like, I don't know, if you're in like the year 1000 BC, you're like, oh, how does everything work? You're like, maybe it's all made of water. But like it's not obvious, like what even are the questions you're supposed to answer?
Yeah.
Whereas now if you're a physicist, you're like, okay, here are the subfields of physics. Your job is to come up with a really good differential equation.
Yeah.
It's probably going to be second order. So that's kind of the difference between, hopefully that wasn't really an explicit definition, but hopefully that gives you a sense of the difference between having a paradigm and not.
Yeah, like it feels aesthetically right. I mean, to me, the vibe I was getting from what you were saying was, if you look at something like algebra, like everybody knows how to solve for x, or at least in most equations, if you don't combine exponentials with linear terms and stuff like that. But anyway, so like we all kind of know, when we approach that, we're like, all right, I've got some manipulations. I know what the feel is of this. X might be really, really hard to solve for, and like that, it might be super, super hard, but at least I know the paradigm. I know the problem setting, the sandbox that I'm in. Whereas, as you say, if you start in like, 5000 BC or whatever, there's no notion that X is something worth solving for, or you might want to find X, but have no idea how it interacts with different things, or even the paradigm of solving these equations. So your view is alignment is more like that, eh?
Yeah, I think we don't really know what the, like I think there are like promising avenues to go down, but I think like a lot of them might be dead ends. I think we're not certain. Like there's this question like suppose you want to not die of AI, right? The way you need to do that, like in order to be like really confident that you're not going to die from AI, at least from a sort of I don't know, maybe from a physicist mentality or from this like inside construct models mentality, is like, okay, what are all the ways in which AI could kill me? All right, now I need to make sure that none of those happen.
Right.
And like, how do you know that you've thought of all the ways that AI could kill you? Well, one way you could do it is you solve 5 problems and then you create super intelligent AI, and then it doesn't kill you, and you're like, oh, okay, I guess that was fine. That's like a little bit risky.
Yeah.
Like another way you could do it is like, okay, here's my computer program for AGI. Like it's written in Python. It has all of these like really nice variable names. It's got the like logic subroutine and it's got the goals subroutine, and I can reason about that really carefully. Unfortunately, that's not really the state the machine learning is in. So yeah, I think like everything is a little bit. I think if you really, yeah. By the way, I think if you think that like machine learning is not the way that AGI is going to turn out, and you're like, oh, I know how we're going to build AI. It's going to be logic databases with probabilistic programming and such. Then maybe you have a paradigm, or maybe you're in a position to get a paradigm. But if you don't know, or if you think the answer is machine learning, but machine learning is confusing, then it's just a lot harder.
This seems related to me to the, because I've seen a lot of people argue that interpretability and clarity and like our ability to understand what these systems are doing is really inextricably linked to safety. Like Chris Olaf, for example, at OpenAI, I mean, their safety team and their clarity team go arm in arm. This idea of this 1-2 punch between clarity and safety is really interesting. Is that sort of what you think this points to as well? Like that there's a dual kind of a dance between those two that's important?
Yeah, I mean, I think. Yeah, so I basically work on I try to have my research go towards helping make AI more transparent and easy to reason about. So I kind of would say this, but I do see them as being at least logically inextricably linked, or like logically very tightly linked. That being said, most of the work that's done on interpretability is not really done by the people who are like really worried about existential risk. So they're I think they're less sociologically linked than they are kind of linked in terms of what things you need to get done.
You brought up your research, and I think one of there's so much cool stuff that you're doing, and I was going through the papers you've worked on, and no problem. Thank you for actually writing them or for doing the research. But one of the things I really wanted to talk about was this clusterability paper that you put together. So can you explain like what is clusterability? Like what's the problem setting? Then what is clusterability, and how can it help us understand what AIs are up to or how they're built?
Yeah. So here's the problem setting. Imagine you have a neural network, right? You've trained a neural network and you want to know what it's going to do in reality, right? Like currently the main way you like get the main way people try to attack this question is they look at, okay, what was the, I don't know, loss or the accuracy on a training set or on a test set that I didn't train on, but I like carefully curated. And like, I think that should give you some pause is the real world is like not necessarily going to be like that test set, right? Maybe you didn't collect all the data you could have. Maybe the real world will change once the AI is, once your big fancy neural network is there in ways that are hard to predict. Like people might be trying to game it, or it might be like shaping the world in interesting ways. Maybe entropy is always increasing. Large composite numbers are getting factored, and like they're not factored today, but they will be tomorrow. So the future just does look different from the past, which might give you pause at the idea of like extrapolating performance from kind of past trends. So what can you do about that? Basically, I think that what you probably want to do is look at your neural network and be like, okay, how does this work? What is this doing? Like, can I understand the operation of this thing in order to get some guarantees about it? Or if not guarantees per se, then maybe like high confidence, reasons to believe it will do good things. And maybe it's not you, maybe it's a computer program. But like, okay, so my way of thinking is like, how do you understand things? I think mostly you understand them by like taking them apart into bits. And like by saying, okay, like here's the world, I live in this world. It's like got a bunch of things. But like there are a bunch of things that I can think about like separately, at least for a short period of time. So like when I think about like the theory of electromagnetism, and I think about like earthquakes in San Francisco, they basically like don't interact, which is good because if everything interacted, it would be like really hard to like when things are on their own, they're sort of easier to think about. So basically because of that, I thought, yeah, I got interested in this idea of, okay, what if your neural network, you have to understand it. It would be easier to understand if you sort of broke it up into bits. And you had smaller bits, and they had fewer things interacting within each bit. And maybe somehow you could have a better job at figuring out what's going on in those.
Can I try to butcher this, by the way, just to make sure that I roughly have the right idea? So just by intuition, comparing to the human brain, and there are going to be a whole bunch of issues with comparison, but something like can we understand the function of a brain by breaking it down into like subbrains, if you will, parts of the brain that are responsible for like some concepts or some computations? Is that fair?
Yeah, that's kind of the idea. So you might think like, oh, neuroscientists have discovered this like language processing area, or this this vision processing area of the brain, and maybe that makes it easier to understand the brain's computation. Unfortunately, that's like really not good enough. Like imagine you like have someone's brain, and like you want to figure out, are they ever going to commit mass murder?
Right.
Like knowing that there's a language area is not obviously, like, it's probably step one of like 50.
Yeah.
But it's not like, it doesn't really do the job. So it's actually, I actually consider that a bit of a like not the most promising comparison in the world, but that's roughly the idea. And in particular, like the thing that I'm interested in is like finding this out just from the weights of a neural network. So one thing you could do is like, okay, I'm going to give my neural network a bunch of tasks that I think have to do with language and see what neurons light up. That's not what I'm doing because I'm sort of vaguely distrustful of anybody's ability to do this. What I'm interested in is, okay, can we just like see if the neural network has like regions that are not very connected to other regions in the network, like where the weights are really small and where therefore you might have some reason to think like, oh, they can't be influencing each other much. So in the paper Clusterability in Neural Networks, I basically quantify this for various neural networks that you could train. So I think it's kind of cool. We do things from the level of a little MLP on MNIST to Inception v3. And we kind of say, okay, in what ways can you carve this up? And in what ways is this like better than random? Like if there were just a random collection of weights, like as long as they're different, you can try and cut the like low connection weights when you're dividing the network into pieces. So are we like more clusterable than random? And the basic result is that like you are more clusterable than random, but you're not so clusterable that like it's you have this like great way of incredibly like neatly carving the network into bits.
Is there a metric that you use to kind of quantify clusterability in one number?
Yes, we use this thing called the normalized cut metric. That was actually developed by another person at Berkeley, Professor Jitendra Malik, back in 2000s. But what we do is we say, okay, take one way of dividing the network into bits, right? Now for that way, look at all of the weights that is kind of crossing the boundary between like that group of neurons and like the outside, any other neuron.
Yeah.
Take the ratio of that to essentially all of the weight that's like inside the weight of connections from one thing in the group to another thing in the group.
Do you have a name, sorry, for those densely connected kind of clusters? Structures?
Yeah, I call them clusters.
Cool. Okay.
Really, you should only call them clusters when they are in fact densely connected. I guess partition elements is my kind of clunky name for describing them when they might not be clusters. So you take this fraction of like the weight that is kind of crossing your boundaries to the weight that is not crossing your boundaries. That's not exactly it, but it's approximately it. And then you say, okay, take the average of that over all of the partition elements you have. And then, okay, how can you draw the boundaries that minimizes this number? So what's the like best way of cutting this network into bits by this metric? Okay, that's what our that's how like divisible the network is.
And do you find that these structures are that they reflect specific concepts? I mean, I guess it would be too early to tell probably based on the research you've done, but are there hints of that?
Yeah, so we've done a bit of, so this is actually like what I'm trying to get into research-wise this year. So hopefully in the future, I'll have better answers to this question. I can tell you what's not the case. it's not the case that they're like suppose you're doing MNIST classification. I think we've basically ruled out the idea that like there's one group of neurons that's responsible for the number 5. That doesn't seem to be what's going on. We are getting some promising results for the idea that like, oh, maybe like there are some clusters, some groups of neurons that we're finding that are responsible for some kind of pattern. But it seems to be like a little bit lower level. But yeah, I'm looking to answer this question this year. But unfortunately, so far, I don't have a great answer.
No, I mean, that makes perfect sense. Just the fact of having discovered that sort of greater than random structure is itself interesting. I'm curious about how this relates as well to like our assumptions about the way reality is. Because so when we put together a convolutional net, right, we kind of immediately make a series, actually we build these clusters ourselves, right? We say, okay, we're gonna assume that there are some neurons that have 0 weights. Like that's how you define this kind of window that scans across your object. So you have this window that's densely connected stuff and then zeros everywhere else. I guess you were working with fully connected, no, you mentioned I think as well vision, right? So were you doing some convolutional nets too?
Yeah, we used both fully connected networks and convolutional networks. We tried both of them.
And was there a difference there? Did you find one would tend to like have a better ratio of the structure you just described?
That is a good question. I actually don't know. So it's a little bit confounded because like suppose you have a network that is really deep, right? Well, then one way you can kind of cut it into bits is to just like get the first quarter of the layers, then the second quarter of the layers, then the third quarter of the layers, and then the fourth. And like as long as the network's really deep, like you're not cutting that much by just taking the first 4 layers, or the first quarter of the layers if there are a bunch of layers, and you're only cutting like 1. So and like the convolutional networks we were looking at were a bit we didn't focus on doing this comparison. But we did find some kind of interesting things in convolutional networks. But it's also the case that we weren't like so this thing where you have like these different convolutional filters and like it's not kind of fully connected. We were kind of not the way we analyzed those networks was a way in which like that kind of modularity or that kind of divisibility like didn't really count for us.
That makes sense. Yeah. I'm sort of curious about what this does to this kind of fuzzy boundary between the assumptions that we wire into models. So when we look at computer vision, we're hard coding this assumption about what it means to see stuff, and the fact that a convolutional filter can be the same filter, and it scans the whole image, and the same filter is going to be equally useful across all parts of the image. And that's like this assumption that we force the model to reflect. And when we have a dense net, we don't do that. So the network is forced to kind of, if it's ever going to learn that, it's going to have to learn it from scratch. And so there's a sense in which when we use a convolutional net, what we're really doing is giving our model a big leg up. We're saying we know these things to be true, or we think these things to be true about physics. So like, let's give you a leg up, kind of teach you this from scratch, and then you can do the rest based on that. And I guess I'm curious about like, naively, I'd expect the more of a leg up you give a model, the more interesting structures it can then focus on developing, maybe, or that's like the vague intuition. So I guess I might guess that convolutional nets maybe would have a more interesting, I don't know, this is obviously a clueless guy throwing something out there, but.
Yeah, I mean, so one confounder there is the convolutional networks are just better at classifying than most ML. So yeah, maybe one question you could have is like, okay, suppose you have a convolutional network and a fully connected network that have the same degree of accuracy. Do we see a difference in how interesting their the structures you can find in the MAR? And the answer is I don't know, and I probably won't find out. There are lots of things to find out, but I do think that's an interesting question. Going to your border theme, I do think it's interesting this degree to which like you kind of we somehow like build certain assumptions into the model, or like certain ways of thinking into our machine learning models. And like on the one hand, I don't know, we have this blog post, The Bitter Lesson, or there's this idea floating around. that is not exactly the idea in the bitter lesson. But there's this idea floating around that, like, look, the way you're going to get smart things is just have them learn all the relevant structure on their own.
Yeah.
And convolutional neural networks kind of spit in the face of that, right? Like one of the most interesting things we're building in, like, why shouldn't the model be able to learn that? But I don't know. I do, on the one hand, I do think it's totally sensible to like if you really believe in structure, like, build it in. There's no reason to like be this kind of super masochist. If you just want to do something, like, build the system which does it best. On the other hand, I do think that you do want some flexibility. So one thing I'm particularly interested in the context of clusterability is like, so networks that you train normally, they're a little bit clusterable, but they're not as clusterable as you'd really like if you wanted to say, like, to make it like really strong claims about how the network worked. So one thing I'm interested in doing is in like regularizing for this kind of structure.
Oh, interesting.
And like, in particular, I think this is kind of an interesting approach because like you have this, there are definitely people who design modular networks. So like, I think there's this paper where they designed this network to play StarCraft, and they have like one unit that does one thing, and one unit that's one network that's like designed to do one thing, one network that's designed to do another, one network that's like designed to like gather all the information from these subnetworks and like process it. So, but that has the pitfall that, like, on the one hand, if you know what the right modular structure is, then you can just do that. On the other hand, if you don't, then I think there's something nice about like having the network learn it. Also, if you regularize for clusterability, then you might get a lot of it rather than like a, statistically significant, but maybe not practically significant amount. So yeah, I think this idea of like, how much do you want to push this? Like if you want networks to be clusterable, how much do you like want to push it on them is kind of an interesting idea that has come up in my research.
And it seems to kind of speak to this question of compute usage, right? I mean, in a scenario, and I think it's no coincidence that like we've been able to make progress on computer vision in an era with relatively limited compute power available because we made all these assumptions. It's kind of a mirror image of, or a continuation really, of what we saw in classical data science, where we went through this era where humans had to do all the massaging, all the feature engineering, and then like have these pristine features that you feed to a logistic regression or an SVM, and then like, oh good, it's doing that last little bit, that last mile, and now we're sort of gradually offloading in an almost continuous way, it seems, our cognition to machines by doing less and less of the kind of prior fixing and tweaking and moving towards, I guess, more generalizable architectures like transformers and so on. But what I find fascinating about this is like you're sort of playing with that interface where you're getting the, by regularizing or by forcing these models to take on more structure, you're kind of allowing us to peek in without having to do that tweaking. It almost seems like that would force us or give us the opportunity to learn new things ourselves about how the world is organized. If this thing like learns new abstractions or new concepts that humans don't tend to lean on.
Yeah, I mean, you might hope. So yeah, I actually, so you mentioned Chris Olah earlier. He has this idea of microscope AI, which is like, oh, what are we, like, there's this question that you have if you're really worried about AGI, which is like, well, what's it good for? And there's this idea of like, okay, here's what we're going to do. We're going to like build these networks that are really good at some tasks. And then we're just going to learn, we're going to like inspect them. We're going to understand their weights. And then we're going to learn some things about the real world. And like, this is kind of what happened in Go. So like we have this, everyone in the field of AI, at least, has heard of AlphaGo. So we have these networks that are really good at Go. What people might not know, but probably could have inferred, is that there's been further work since AlphaGo. There's this thing called KataGo, which is like this publicly available network that you can train with, and we have tons of these bot versus bot games where the bots are like higher level than humans, and so we know some things. We have some new ideas about Go. Right, we have like some new opening tricks and like a new sense of like, oh, here are like some heuristics that we're just looking at from how the thing plays, which is nice. But like, I do wish we could look at the networks and be like, okay, what is this thing thinking? What does it know that I don't? That is, or is it just one thing, or is it like, oh, it's just like really good at reading, or there's like it's some really complicated answer that you can't say. Especially like Go, right? It's this case where we know like the best models, they're not pure deep learning. They do use this Monte Carlo tree search thing. I don't know whether like if you did inference without MCTS, they would still be superhuman. We know the domain of Go. It's not like how to live a good life or what's the action space. Go is like pretty pinned down. We know what it means to win or lose. We know what all the moves are. Like you would think that that once you train a thing that's really good at Go, you could then gain a ton of insights. But in practice, we have to do it this way where it's like, okay, the only way we can learn things is if we set up a board state where the answer, the thing it plays on the board is the answer to our question about like the true nature of the game of Go. It's like, oh, is that really the best way that we can come up with?
Yeah, it's almost like we're only able to speak in the language of the very final layer of the network and say like, okay, we can understand your outputs. That's human understandable. But the minute you start to move into the network, there are thoughts happening, presumably, if I'm not anthropomorphizing too much here, that that are like not human tractable, and that seems like both a wasted opportunity. And actually, I think that's a good sort of maybe that's a good note to close on as well. Just this idea that it's not clear, at least, that they're necessarily that safety is like clearly a tax on capabilities all the time. That as these systems get more and more capable, our ability to get value from AI is actually going to be limited by our ability to very specifically indicate what we want. Obviously, this is this would be a controversial view. I'm not even sure if I agree with it, but I'm curious what you think of that.
It's definitely sort of, this distinction between like safety and capabilities, where the idea is that capabilities is about getting AI to do more impressive stuff, and safety is about like making sure that it doesn't, ruin everything. It's one of these distinctions that I think is kind of fake, but also kind of profound. So it's definitely not the case. Like sometimes people are like, oh, do you do research on safety or capabilities? And I think that is kind of a fake distinction where like, a lot of stuff like transparency, I think I kind of think of them as two different objectives, and research can like contribute to those, objectives in like different ways. So in the economics I learned in high school, there's this idea that imagine you're a country, right? And there are two things you can produce. You can produce computers or genes, right? And like if you put all of your effort into producing genes, you could produce 100 genes and 0 computers. If you put all of your effort into producing computers, you could produce like 50 computers and 0 genes. And if you did a mix of both, maybe you could produce like 49 computers and 80 genes or something. And like there's just this like, if you think about an XY plot where X is the number of genes you produce and Y is the number of computers you produce, like there's kind of this curve that like slopes
like a
down.
Or quarter.
Something like that. I don't know how good this
maybe it's
is on audio.
Or
so some kind of thing. And like at a fixed level of technology, you can move across the frontier, right? So there really is a trade-off in the sense that like right now, with the knowledge that we have now, we can like go for broke in producing something that's really smart, or we can make sure that absolutely nothing bad happens, but like we can't really do both. But you can move that frontier up, right? If the country like discovers, if it figures out how to make a factory that produces genes like for half the cost, for half the like number of workers, using half the material that like the old factories used.
Yeah.
Well, then that moves the curve up. Like with the same number of computers, you could produce more genes, or if you could produce the same number of genes with these like cheaper factories, and then you use all those workers and all of that like steel or whatever to make more computers. So steel being in the machines, not in the genes, I hope. But basically, I think that like there totally is this idea of this moving production possibility frontier for safety versus capabilities, where like, if we figure more things out, hopefully we can get AI to do more impressive stuff in a more safe way. And like, I think that should be the dream. Like, AI, if we had things that were much smarter than us and like were really useful to us, that could really change the game, I think. So I don't know. I do think we should be looking at like how to move the production possibility frontier further, up and to the right. And also, what do we where should we be on that frontier is a different question. Where
Yeah.
perhaps I would urge safety more than other people might. I don't know.
I mean, that makes sense to me. Like one, I think, source of tension in the AI safety, AI alignment community that I think I've perceived is like there's one camp that says, as Eliezer Yudkowsky recently tweeted, like, look, you've got the thing with intelligence, super intelligence, is you've got one shot. You do it once, it's more intelligent than you, and if you screw it up, basically it's game over. There's no redo. You can't learn from your mistakes and try better next time. So we really do have to anticipate everything that could go wrong. And then the other side is like, well, can we make a superhuman AI that can help us to align AIs? Can we make a narrowly superhuman AI in some sense, which I believe, and I don't want to speak for OpenAI, but having spoken to a couple folks in that ecosystem, it seems as though that's a big part of the philosophy there is like, let's try to get a theorem proving AI. Let's try to get things that can actually help us make progress faster than humans could.
Yeah, I do think there's that distinction. I mean, yeah, there definitely are some groups that are like trying to create really big language models because they think, look, there's some research that you can only do on really big things. And yeah, what do I think about that? I guess I don't know I honestly don't know what the right answer is. I do find myself a little bit, I think if I were founding a research organization, I would probably not put a ton of money into making really big capable models. But yeah, I don't know. There is this question of like, yeah, how much, I think it goes in part to this question of like, how much warning do you get before you have before you have like the Terminator or whatever?
Yeah.
Do you go like 1 month before you have the Terminator, do you have like a mouse or do you have something which is like 3% less good than the Terminator?
Right.
If it's 3% less good, then it's a little bit less like you have. It's a little bit, you can like the problems maybe don't like qualitatively change a huge amount, and like maybe you can try and solve them as you go on. But even then, I don't know. If I think about like how good is humanity at solving these problems that like creep up, I'm like, not the best.
Yeah.
Not as good as I'd like them to be. But yeah, if it's the case that like a month you had nothing, and then you have like a really smart thing, and you've got like, and if you have the ability to build this really smart thing, then maybe 5 days from now, someone else has the ability to build a really smart thing. It's like, oh, that's a much harder situation. And yeah, I don't know. I think it's kind of hard to figure out which one is actually going to happen.
Well, and that kind of makes me think as well about the pace at which we're adding compute and size to these models. Like, it's not like we're going, like OpenAI is releasing an incrementally like 5% bigger system every week or every month. Instead, they're going from like, 1x to 100x to 10,000x, and we're leaping way over these like orders of magnitude, which seems...
I mean, the good thing is that that'll stop eventually because
Right.
At some point, there isn't enough computation available in the world.
Yeah.
I don't know if that's good news or bad news. But yeah, like if you look at these like scaling laws for just how much computation is being used, they just are literally unsustainable unless we like, quintuple Moore's law or something instead of having it slow down. Yeah, I do think that we're definitely seeing big like leaps in like performance. Or sorry, that's the opposite of what I wanted to say. We're definitely seeing these massive leaps in size. It's not obvious that like GPT-3 was like 1,000 times more useful than GPT-2. I kind of don't know how to think about like what that scale.
Yeah, I agree that that's a super confusing thing because like it does seem to be the case that GPT-3 has economic value that's orders of magnitude greater than GPT-2, but at the same time, like I don't know, I very much resonate with what you're getting at here because economic value it's an important measure too because companies that can do this can generate more revenue and therefore scale systems faster as well. So there's like an interaction there. It'd be interesting to see more thoughts on measurement. I think Jack Clark is doing a lot of that over at Anthropic, sort of focusing on measurement of AI progress too. Maybe that's a good place for us to park the thought on a forward-looking note. I do want to plug, so for anybody who's interested in Dan's work, research, and the interviews that he conducts, he has a podcast called Excerpt. Excerpt? I'm pronouncing that right? Sorry, Excerpt. So AXRP, it's a really great, I've actually listened to all the episodes. They're really good, great exploration of sort of existential risk research, alignment research with a bunch of different researchers. We've had Evan Hubinger on. Dan's done a great interview with him about inner alignment, so please do check that out. Dan, is there anything else you want to plug? I know you've got a website as well. I'm not sure if you're interested in sharing that.
Yeah, I mean, I have a website. If you're interested in what papers I've published, you can read my website. Yeah, the website also has a blog. It's called danielfilan.blog. Yeah, I think the thing I'm most excited about is like if people listen to my podcast and then if it's really bad or useless, tell me why. And if it's good, then hopefully your life will be moderately better.
I think if anybody who's listening to this right now finds themselves interested in pursuing AI alignment research, I think there's a lot of great stuff on Daniel's website for you to kind of get started with too. So dig through those papers, dig through as well some of his co-authors. Like he's in the thick of it, so this is really worth doing. And certainly, well, Dan, I mean, I don't know if you're open to Twitter DM stuff like that, but I'm volunteering your inbox. No, feel free to reach out to me in any case, just like for routing purposes and whatnot, as always.
Yeah, I guess I could currently stand to have a doubling in the number of people who contact me, but I don't think I could stand to have a dectupling. So
okay, you heard it here, folks.
Govern yourselves accordingly.
2x. Let's 2x Dan's Twitter inbox here. All right, awesome. Thanks, Daniel. This is great.
Great to talk to you as well.